Okay, let's continue. Sorry for I have some technical issue. But so anyway, so let's see. Let's continue. So we have this region somehow, and if you remember how to, maybe I should write down something like this, um, where our region, I mean the base region. Be careful. This is the base region, which is this. Right. So this is D. And if you remember, this is just square root 3 and square root 3. Okay. So this is actually this, the left, the picture on the left is the whole region on which we integrate basically. But at the same time, we have a kind of a base region in R2. So everything is fine. So let's see. Okay. We have exactly the same idea as before. Remember, since we start with dx, dz, what does it mean? We just consider x and y parameters are fixed, right? Therefore, actually, we start with a kind of a slice. Okay, now we start with a kind of a slice parallel to z-axis. Therefore, the picture is something like this. So we start with some fixed x and y, so which is fixed, and we have a kind of a slice like this, and this hits the region, and it's passed through the region inside, and then it hits the region once more, and it lives. Okay, this is the red. The green one is the first. Actually, it's basically encodes the first part of the integration. And as you see, I mean, if you look at carefully, the equations, I mean, the red one, the red surface is just a sphere, remember, and this red part is given by this function. Be careful. Okay, because we are just looking at the upper part, so we can write down as a graph of a function, but at the beginning, I mean, in the first place, it was not. And this blue one is given by this equation, the graph of that thing, right? So everything is fine. And now just focus on those green points. So the first green point is exactly hits our region when z is this, and the second one exactly leaves the region when z is that much. Therefore, z ranges from this much to that value. Okay? Therefore, maybe I should write down our strategy. So just the meaning of this iteration, that this order is start with a slice which is parallel to z-axis, if you like. Okay, and actually, and then as before, remember, first start with a horizontal slice and move it vertically, or vice versa. But now we start with a slice parallel to z-axis, and then we are going to move this slice along the region D. Okay, and then move it along the base region D. But the second part, I mean the motion through the region D is actually controlled by the usual, I mean the horizontal and vertical slice business. Okay, and this part and the second part actually, so this second part is just using horizontal, vertical, or maybe rays, slices, or rays as before. Okay? Fine. Now we just, therefore we have more things to do. So let's see. I mean, just try to fill these two, those slots, right? So therefore, we are going to use now our standard horizontal and vertical slice business. for this, so let me just start with a kind of a slice like this, right? You see this slice enter the region over here, leaves the region over here by starting with a fixed y, because remember our next order is dx, therefore y should be fixed, if you like. Okay, and this is exactly the point where it satisfies basically y equals square root 3 minus x squared, right, with a plus sign, be careful. And x actually ranges from therefore 0 to x equals square root 3 minus y squared, so as before. And then we just have 0 to square root 3 minus y squared, and as a final touch, as before, we just move this horizontal slice vertically, and as you see, y basically changes from y equals 0 to square root 3. Okay, so that was the strategy. But now we have some extra slicing thing, and then we just follow the same strategy as before. Very well. So what about part B? Now part B, we are going to use the cylindrical coordinates. So we just let x equals r cosine theta, y equals r sine theta, and z is just z. Okay. Then with this new coordinates, we get the following observation. So we have this equation, if you remember, it defines something, but now this turns out to be r squared, right? So this turns out to be r squared, and also we have another equation. Remember this one, I guess, right? But now this becomes, in the language of r and theta, 12 minus r squared. And of course, remember, we translate everything. Therefore, we have a new volume element, which was dz r dr d theta. And this gives you how to construct your iterated integral. So this gives you basically the order. Okay. So let's see then. So let's see what we have. So we have the following. So our integral. So we try to write down the iteration. Oh, just a second. Oh, okay, no problem. Okay, we have some integrand over here. We don't know what it is, and we don't care actually. But now, since we just replace x, y, z with those expressions, of course, f now turns out to be a kind of a function, depends on r, theta, and z. Now we have dz, r, dr, d theta order. Now, remember, if you go back and check part A, actually it is easy to see that now we have r squared here, because instead of x squared plus y squared, which is expressed as r squared in r theta coordinates, and in r theta coordinates we have this. Okay, we just replace those expressions over here, if you like. So this one, I mean, maybe I should okay, anyway, so this one and this one. Okay, okay, everything is fine, but now the rest is about analyzing the base region. But here remember, our base region is just something like this. Okay, square root 3, square root 3. But now, instead of using standard xy coordinates, remember how to deal with polar coordinates. Just throw some ray. Okay, so by throwing rays, something like this, just throw some arbitrary ray like this. Okay, it hits the region over here and starts over here. This is exactly when r equals 0, and you have some defining angle theta here. And this part is exactly, the point is exactly when r is that much. But this is just square root 3. Okay, therefore r changes from 0 to square root 3, and at the same time, I mean, if you look at carefully, so what is it? So you have possible rays like this, like that, like this, and overall possibilities. Of course, you end up with, I mean, in order to scan the whole region, you end up with this one and that one. And this is exactly when theta is 0, and this is exactly when theta is pi over 2. Okay, you just rotate this slice, right, along the region, and therefore theta ranges from 0 to pi over 2. Okay? Okay, fine. So what about the next one? Okay, spherical coordinates. Now we are going to write down everything in the language of spherical coordinates. So C. Okay? So just recall the spherical coordinates. So we should remember what are those. Maybe I should sketch something like this. So we have a kind of a sphere like this, and okay, and let's say this is our coordinates axis. Okay, fine. Okay, x, y, z. Similar idea. We just throw rays. Okay, we just throw rays and it hits the region and it lives. Okay, and we just analyze exactly this picture. Okay, so for instance, this projection over here like this. Okay, and we can see the all coordinates. Okay, this is exactly z, x, and over here y. Okay, maybe I should make it more even bigger. Okay, so this is the picture actually, if you like. And if you look at carefully, we have some possible angles, defining angles. So this part is exactly, let's say, phi, the angle phi, and this is exactly the angle theta. And also we need another extra information, which is rho. This is the length of that thing, rho. Okay, and if you remember, with those things, you can easily compute, I mean, for instance, this part, I mean, this much distance is just rho times cosine theta, blah, blah. And recall that, so let me write down clearly. So in this new language, z is just rho times cosine phi, and therefore it's easy to see, but this part is just rho times sine phi, and it is exactly that much unit, and by multiplying cosine theta you end up with the x coordinate. Therefore we have something like this, and the y is just rho times sine phi and sine theta, and the z is rho cosine phi. Okay, now this is our new language basically. Okay, now these are spherical coordinates, of course, with, remember, by using this Jacobian, its determinant, blah blah blah, you can end up with this volume element which can be computed like this. Of course we just skip this computation, but this was the volume elements. Okay, this is the volume element in, okay, in this new language, I mean this rho phi theta system. Okay, so that was the idea. Now in our case, if you like, so in this weird picture, remember, so what was it? So maybe I can copy it, so over here, because we should be a little bit careful. So let me maybe I can do this, so let me try at least. Let's copy this thing and put over here. Is that possibly? Okay, fine. Okay, remember, this was our picture. Let me make it a little bit bigger because we need this. Okay, fine. So this was, so let me complete the picture. So this is the x part, y part, blah blah. Now the problem is, now we are going to throw some rays as before by using spherical coordinates, of course. But now we should be careful. Why? Because when you throw a ray, can I? Oh. Mm. Just a second. Can we? Oh, maybe this is better. Okay. Let me get rid of this thing. This one is better. Come on. Okay. Okay, something like this. I'm sorry. Okay, fine. So let's go back our discussion. So this is it. This was our region. Now we are. Oops. Okay, fine. Let's see. What was that? Okay. Let's see. Okay, fine. So we are ready to go. Basically, so let's see. So let's try some rays. Okay, so let's throw it that way. Okay, you see it hits the region over here, so you have some angle here. So what if you throw this ray? Okay, it hits this surface, the red one, but the problem is after some points, for instance, exactly when you hit this boundary circle like this, now after that crucial angle, you see now you hit a point with a different property. Okay. What I mean is the following. So when you hit, for instance, let's say over here, this is exactly when, so x squared plus y squared plus z squared, what, equals 12, and this is exactly when rho is square root 12. Okay, but and you have some angle here, but after some angle, which is exactly this one, when you pass this angle, okay, so after that angle, okay, actually the point where the ray hits the region, right, actually satisfies different equation, satisfies different equation. As you see, this the green one exactly corresponds to that thing, rho equals square root 12. But on the other hand, if you cross this line, I mean this one if you like, this is very specific ray, and after this yellow one, when you hit somewhere over here, for instance, what this point is now satisfies a different equation, right? But now, because this is exactly sits on this surface, but in this new language, this thing corresponds to rho cosine phi plus rho square sine square phi, right? When you have certain algebraic manipulations, so you have rho, rho sine square phi minus cosine phi equals 0, and this means that exactly rho is either 0 or rho is cosine phi divided by sine square phi. Actually, this is easy to see because when your angle changes, remember, so you have some angle over here, and when you change this angle that much, for instance, the lengths of each ray, right, you see getting smaller and smaller and smaller. Therefore, you should be careful. But what is this angle? This angle is exactly when, so you can easily compute because, so what is it? This is exactly when, so Z was, oh, okay, Z was 3, okay. Therefore, this much distance is exactly 3, and we know that this is exactly square root 3, therefore this angle is just pi over 6. This is not theta, but the phi. The angle phi is pi over 6. Therefore, we should be careful. When phi is less than pi over 6, and this specific angle, actually rho ranges from 0 to this. So rho actually ranges from 0 to this constant number. But when you pass through this angle, okay, in this part of the world, but now rho ranges from 0, you remember those lengths, but now those lengths depends on your angle, angle phi, okay. Therefore, this is ranges from 0 to cosine phi divided by sine square phi. Okay. Therefore, we need to write down two triple integral. And on the other hand, of course, if you look at the boundary, possible largest value, right? Remember this phi starting from this slice, and for instance, end with like this. Therefore, this is exactly when phi is pi over 2, and this is exactly when phi is 0. And what about theta? And if you look at carefully, theta runs from these two rays actually, and this is exactly when you have a theta runs from, this is exactly when theta equals 0, this is exactly when theta equals pi over 2. Therefore, all ranges are clear now, so let me write down the final result. So after this long analysis, so we have the following. So we get the following observation. First part of the region, as I said, before this critical angle, so we have something like this, okay, rho phi theta, and we have rho square sine phi, d rho d phi d rho theta. But now, as we discuss, now rho, so when your angle, maybe I should use a very different color, I don't know, actually, okay, pi over 6, right? Pi over 6, the critical one. And therefore, when you phi runs from 0 to pi over 6, actually, when you do this, rho, as we discussed before, ranges from 0 to square root 12. And on the other hand, and theta is just runs from 0 to pi over 2, so it's not that much interesting. But now, plus the second part after this critical angle, phi, okay, these are the same, square phi d rho d phi d theta. Okay, fine, but now we have a problem, right? Because after this angle pi over 6, right? So after this angle, we have different types of points. Okay, so the ray basically hits the surface, okay, in a very different point. So previously the point satisfied the equation of a sphere, but now point satisfies actually something else. And now this ranges from that thing, but now rho, as we discussed over here in this blue part, and the rho now ranges from 0 to something else, and this thing basically depends on the angle phi. Therefore, your rays is phi getting larger and larger and larger, your length of your rays getting smaller and smaller and smaller, as we see in the picture, right? You see this orange ones, depending on phi, getting smaller and smaller and smaller, their lengths. And on the other hand, we have again a quarter turn, therefore theta again runs from 0 to pi over 2. Okay, fine. As you see, it's a kind of a long analysis, and after this long one, we got this result. Okay, therefore we should be careful. Okay, therefore we should be careful while using spherical coordinates. Okay, so what type of points we are dealing with is the important part of the story. Okay, so this ray, so we just throw some rays, okay, and ray starts from somewhere and it's somewhere else, but where it hits basically is important, okay, over here, because it changes after some critical angle. After this, the yellow one, after the angle pi over 6, it actually changes, okay, because now we have different types of points. Green points before this angle, the green points satisfy the equation of sphere, but now we have blue points. Blue points satisfy the equation of paraboloid. Okay. Okay, fine. Maybe before the next one, let's take a short break. Okay.